present is more general than that. I'm going to give an overview of where we are in hydrological science in terms of providing the data and models that we require to solve water management in mining problems. And in doing that, I'm going to touch upon some of the research that I did prior to coming here at Imperial College. So you've heard a bit about my background, so I'll skip over that. So the context for this talk is really the risks that are associated with floods and droughts. Now in the UK in the last 10 years, it's been a very flood-rich period. We've had major events such as Boscastle and Gloucestershire floods in 2007 and 2004. Now, the UK has an extensive system of flood defences, but actually such are the risks these days that the government can't afford even to maintain the existing system of flood defences. So they're looking for more clever ways of managing flood risk. And that's been good for us researchers, because in order to find these clever ways, they need top scientific minds to study the hydrology of this. Now, of course, this is relevant to mining as well. Mining suffers from operational interruptions, loss of equipment, and perhaps risk to life, and then significant environmental disasters associated with floods. Droughts as well of concern to the mining industry. So this is just an arbitrary image from the Australian Bureau of Meteorology website. Just illustrating that droughts have become a major issue in Australia and causing tensions between different sectors competing for the water. So what I'm going to do now is just cover a few slides which talk about the nature of hydrological variability, the difficulty of characterising that, and the implications for our risk estimation. So ideally, what we'd be able to do is study this hydrological cycle, and at any point in time, any point in space, be able to predict how much water is present, how fast it's moving, and in which direction it's moving. But largely, hydrology appears random. So even the basic laws of physics, such as mass balance, energy balance, Newton's law, so in other words, water flows general downhill, some of these even appear to be broken by what we actually observe, simply because we're not observing the complete picture of what's actually happening. So the traditional design methods to cope with this variability are just to do a statistical analysis of the variables of interest and represent variability as a probability distribution. So this example here is just from some work we did for Thames Water in England, looking at variability of drought indices for the Thames River. So you basically get a probability density function representing degrees of drought in the Thames Basin. And so from this, we can take any severity of drought, we can attach a probability of reoccurrence to that severity of drought, and then we can look at the hazards associated with that drought and turn that into a measure of risk. And almost all designs and planning for floods and droughts nowadays is based on this kind of risk evaluation. So just to illustrate some of the difficulties of doing this, first of all, this kind of analysis, deriving probability distribution, in general assumes that you're looking at a stationary system. So in other words, the data that you observed historically that has allowed you to derive this probability distribution represents the existing system and how the system is going to be during your planning period in the future. But for various reasons, due to natural variability or some kind of human effects. There tends to be trends in our hydrological systems, and they could be simple linear trends, as illustrated in this slide, or they could be more complex non-linear trends. And then often on top of that, we have some identifiable cycles. For example, Australia, of course, is affected by the southern oscillation in the Pacific Ocean, which causes decadal scale cycles. And then on top of that, we've got some apparently random fluctuations in hydrology. So when we're deriving our probability distributions and doing our design from that, there is of course a danger that the data that we're basing this on is not representative of the full historical picture. For example, typically we'll use between 20 and 30 years of hydrological records to derive a distribution, and that may not cover even one full cycle of these oscillations. Okay, so what can we do about this? Well, of course, we could wait another 20, 60 years, whatever, and collect more data. We can try and reconstruct historical data so that we've got a longer record beyond our actual measurements. And what we can try and do is actually understand the hydrological processes that cause these trends, cycles, and apparently random fluctuations, so that we can actually tell what stage of this cycle, whether or not there's a trend, and therefore be able to recognize the limitations of the data that we're working with. And of course, once we've got that process knowledge, that gives us the ability to actually project what's going to happen in the future under climate change, land use change, and other types of change. Another potential problem is that the actual nature of the variations, of these apparently random variations, may be changing in time. So this is a recent example from the UK. Now, 2012 was a very unusual year in the UK in terms of the hydrology. So this slide shows the total river flow in the UK. So this is observed flows from all the major river basins in the UK, just added all together. So it's plotted over the year 2012, and this pink area represents the minimum historical recorded aggregated flows in the UK. And then this blue area represents maximum ever recorded flows, and then this black line represents the 2012 flows. So what you see here is that 2012, we were in the worst ever recorded drought in the middle of March. And people are beginning to panic about this because the Olympics coming up and things, and seriously getting short of water after having had two very dry winters in a row. But what happened then was just over the next month, it turned into the wettest ever year on record. So the statistical probability of this happening, changing from the driest ever observed conditions to the wettest ever observed conditions in a period of 2 months, is so low that it implies that the actual nature of variability has changed. And these kind of extreme changes are being observed all over the world. And of course, this causes us to question whether the probability distributions that we've derived in the past are actually applicable to what's going to happen in the future. Another thing, just to mention in passing, just to illustrate the scale of the UK compared to the scale of Australia. Remember, this is the total flow as aggregated to the whole of the UK. The flow in the Brisbane River in your 2011 floods was 11,000 metres cubed per second. It's one of the nice things about working in Australia, everything's bigger, better. Spatial variations are also relevant to us. Now, if the nature of hydrological variability was relatively uniform, then it would be relatively easy for us, because we could observe some sites in detail for a long time, and then transfer that knowledge to other locations that we want to look at. But hydrology is not that simple. We get significant changes in the variability over space. And sometimes these variations are relatively easy to understand, and this is just an example of the very extreme variations in hydrology from the Chile and the Peruvian coast in the Atacama Desert, and then the strong gradient in rainfall when you get up to the other side of the Andes and to the Amazon basin. But very often the spatial variations that we observe, we really don't understand at all. And I'll touch upon that again later in the presentation. Another problem that we've got, even if the measurements we take are representative of what's going to happen in the future, the measurements we take often aren't really very accurate at all. And so just some examples of that. Now you would think river flow would actually be quite easy to measure. In fact, it's one of the easiest things for hydrologists to go out and measure. But to do that accurately and to do it continuously over a long time actually is expensive and difficult. So this example here shows construction of a permanent gauging station somewhere in the UK, I can't remember where. But what's needed here is a very major diversion of the river with significant environmental impacts, a construction period of about 12 months, and a cost of who knows how many hundreds of thousands of pounds. And once you've done this, well, you have to design these gauges either for low flows or high flows. You can't design them for both. And if you've designed it for low flows, it might give you 3% precision for the low flows, but then you're looking at plus or minus 15% precision for the high flows. So this adds to the uncertainty that we have in our data that we use for design. Now, of course, in most cases, we can't install permanent, expensive gauging stations. We have to do with much more shaky type structures, as is illustrated here in, this is from Oman. And these type of structures give a very variable relationship between the water depth and the flow rate in the river, with typical uncertainty maybe plus or minus 25%. And of course, these are susceptible to damage during storm events as well. There are significant advances in using non-intrusive and relatively inexpensive gauging methods. Now, for example, these days in small streams like this, you can't just go in and build a weir because there's important spawning grounds upstream of this that fish need to swim upstream, etc., etc. And so people are looking at much more non-intrusive meters that you can either position above the river and they look down onto it, or you put at the bed or the banks of the river and it sends a beam of ultrasound across the river. But still, the kind of accuracy we're getting from these is plus or minus 10, plus or minus 20%. Rainfall is another thing that is extremely important to us, but again, difficult to measure accurately. And the challenge in this case is mainly to do with the fact that the rain gauges we use measure rainfall at a point. But rainfall changes a lot over space. And in most cases, really to get an accurate picture of the spatial rainfall, you need a gauge every few hundred meters. So in other words, over a decent sized catchment, you need thousands and thousands of gauges. But typically you've got 5 or 6. And so we're often looking at very high errors in our estimates of rainfall. In addition to that, often where we need to put our gauges are quite remote and inhospitable places. And it can take several hours to get there to do any maintenance to the gauge. So these ones are in Saudi Arabia. These are subject to storm damage as well, sand damage, sun damage. This one's at the top of the mountain in Wales. It takes several hours to get there from the nearest office, and subject to wind damage. We have been working quite a bit on methods of actually measuring the spatial variation of rainfall, so that the main way of doing this is using radars. And we've been looking at using portable radars that were originally designed for use in shipping. But we're putting these on tops of buildings in London and seeing if they can help us measure these convective storms that come across a lot of the flooding damage. But it's going to be several years or decades before really this type of technology is ready to be used operationally. This is just an example of when errors in hydrological measurement become a problem for us in hydrological analysis. So this is one of my projects in Oman, and what you've got here is 4 years of rainfall and flow data, with the rainfall plotted on the top axis and the flow data plotted on the bottom axis. First of all, it shows you it doesn't rain very much in Oman. For example, this year it's only rained twice. And secondly, what you can see from this is a great deal of variation in the relationship between the magnitude of the rainfall and the magnitude of the observed flow. And the best example of that is this one here. This is the biggest flow event in 4 years, and it is pretty much the smallest observed rainfall in 4 years. And so this kind of, this is to do with measurement error, because it just happens in that storm event, the rainfall didn't fall where we were trying to measure it, it fell in other parts of the catchment. And this is an extreme case, but this kind of error does cause us some problems when we try and actually understand the hydrological processes affecting these flow rates. Okay, so just some summary of what I've said so far on hydrological variability. Floods and droughts need to be characterized by probability distributions for the purpose of planning and design. And for extrapolation to the future and to new sites, we need to introduce our process knowledge into our models. Both remain difficult due to trends, cycles, and unexpected changes in behavior and problems with measurement accuracy. And the observations we have are not yet comprehensive or accurate enough to support our analytical capability that we've got. Okay, I haven't said anything about models yet, so I'm going to talk first of all about climate models. And of course, climate models are extremely important to us these days, because almost always in our designs and our planning we want to take into account potential climate change effects. And after that I'll talk a bit about hydrological models and some of the research we've been doing on that. So just to introduce what is a climate model, well, basically a global climate model is a model that attempts to represent the physics of the circulation of water and energy in the atmosphere, in the oceans, and to some extent on the land surface, and how all these interact with each other. So these are enormously complex and expensive models that are run on supercomputers, and there's many climate modeling groups around the world that have developed their own independent models. Typically, the scale of these models is quite large. For example, most of the models in use at the moment, global models, are about 270 kilometers times 270 kilometers. That is the scale of information that they output. Now, these types of models are not very good at predicting rainfall. And the reason for that is that the physical processes that affect rainfall happen on quite small scales, much smaller scales than the 270 times 270 kilometers. And therefore, the climate modelers have to use some parameterization, so in other words, some empirical elements to their model to represent these subgrid processes that produce rainfall. And how to do that is not an exact science, and there's significant variations in how it's done between different models. So what that means is that in many areas of the world, there's significant disagreement between the different climate modeling groups on how much is going to rain in the future. So this is the example of India, where over almost all of India, there's more than 100% disagreement between these climate models. And so clearly, if you're in one of these regions where there's major disagreement, that is going to be a problem for your planning. In England, I'm not sure of Australia, but in England, the level of disagreement isn't quite that high, but still high enough to cause significant problems for water companies when planning water security into the future. So the typical way of using these models is not just to rely upon one model, is to rely upon an ensemble of models. So you've got the IPCC produce these ensembles of projections. So this is a plot of temperature projections into the future up to 2100, and the IPCC range is this green range here. Now the range for rainfall would be significantly higher because temperature is actually quite easy to predict, and the models agree relatively well on that. But then you get some other modelers coming along who say, well, actually, you know, a lot of the assumptions that you're using in this ensembles are actually quite common between all these models. And actually, I've got a different assumption. If you apply my different assumption, you get an even wider range of potential futures. So the global climate modeling is a huge topic, but it's relatively young. And there's a lot of science to be done before it's providing the accuracy of data that we really want for our planning. Now, another issue, of course, is that the scale of the data being produced by these models is not the scale of the data that we need for our hydrological problems. So often as hydrologists, what we'll be wanting is rainfall data at a scale of 1 kilometre squared. And it might be much less than that for, say, urban type applications that might be larger, would be very large catchments, but typically it would be 1 kilometre. And so we've got this problem of taking the outputs from these global climate models, about 250 kilometres, and downscaling them to about 1 kilometre squared. Now there's two general ways of doing that. You can use something called a regional climate model, which basically is a much higher resolution, physically based model, which is run within each of these global climate model grid squares using the same kind of process representations. But at the moment, typically, they just give data on about 20 kilometres times 20 kilometres. There are some attempts to run these models at 1 kilometre squared, but the ones that I'm aware of actually takes 6 months to run the model to produce 1 year of data over a relatively small area. And so clearly, we can't hang around for 6 months for these meteorologists to run their model once. And after they run it once, of course, they might look at the results and say, actually, we're not happy with these results, we're going to have to tweak the model and we have to run it again, so you have to wait another 6 months before you get a better result. So we tend to use statistical downscaling instead. So what statistical downscaling does is, rather than use a very complex dynamic model to do the downscaling, it uses very simple statistical correlations. So the principle is that there will be some correlation between what these global models predict at a very large scale and what we can expect at our much smaller scales that we're interested in. So the details of these equations aren't important now, but basically we represent that using equations that represent the correlation between the large-scale climate and the probability of occurrence of rainfall, and another one representing the correlation between large-scale climate and the amount of rainfall when it does rain. Now, hydrologists, even though we don't claim to be particularly skilled at meteorology, we tend to get involved in doing this simply because we need some way of generating the data for our hydrological models. So we've been doing this at Imperial College in various different applications. So this is just generating some maps of future rainfall in Botswana to help us with reservoir design there. And this is an example in southern England where we've been trying to infill the historical records back to 1850 to help with water resources problems. And then this is an example of the kind of thing we do with that information. So this is looking at reservoir reliability in Botswana into the future. We can then say, okay, let's revisit these reservoirs that were designed under the assumption of stationary climate, and let's look at how often these reservoirs will fail if we consider climate change effects. And of course, because of the uncertainty in the different global climate models and the additional uncertainty in our downscaling procedures, you get very large uncertainty in what you actually project into the future. Some of the projections saying the reservoir will be fine, and some of them saying that it's going to be failing up to 50% of the time in the later half of the 21st century. Okay, so that's just some of the climate modelling issues. Hydrological modelling, I like to use this map that my friends at the British Geological Survey provided to me to illustrate the nature of hydrological complexity. So this is the Thames Basin outlined in this black line. This is a geological map of the Thames Basin. And we've got similar maps representing the drift geology, the topsoil, the land use, the vegetation, the climate, etc., which are similarly complex. And our job as hydrological modelers is to try and produce models that are practical to use, which embody this huge complexity in how water actually moves through a catchment into a river and into groundwater. So there's two basic ways of doing this. There's some applications where all you actually want from your model is the average hydrological outputs over the whole of your catchment. So we call that a lumped model. But more often these days, what we're interested in is the actual spatial distribution of hydrological outputs over the whole catchment. And then we have to use a distributed hydrological model, which typically will involve overlaying a grid like this over our catchment. So the kind of problems where this is important is, for example, if you want to say how far away from a river do you need to put your pumping wells so that they won't have any significant effects on the river. And that is a kind of problem that requires a very spatially explicit representation of the links between your pumping and the hydrology of the catchment. So in that case, we'd want a distributed model. The challenge then is if we have a model which is as spatially complex as this, how do we actually need to understand the hydrological processes in each and every one of these grid squares, ideally. Of course we don't. So then the challenge becomes how do you produce a practical model given the gaps in your knowledge. I've got a few slides now which illustrate what we've been doing on hydrological models to solve some of these problems using a case study of peatland rehabilitation. Now, much of the UK is quite a damp and miserable place and looks something like this. So this is moorlands in northern England. And actually, although it's damp and pretty miserable, these are potentially important ecologically. They're important sources of water. They provide large quantities of good quality water if the catchment is in good condition. But what has happened over the last 100 or perhaps 200 years is people have recognized that the main economic benefit of these areas is to put lots of sheep onto them. And what that does is it changes the hydrology, it changes the natural vegetation, it perturbs the ecology, and of most importance to our water companies, it affects the quality of the water of these areas. So there's now a major interest in rehabilitating these moorland areas. So we've been studying various different plots in these areas, and then we've been developing models that allow us to predict what the optimal rehabilitation strategies will be in terms of the hydrology and water quality. So we've been developing really quite complex models for the plots that we've been observing. But the challenge then is how do we take a really very well-defined model that we've built for a very specific part of this catchment, and then how do we upscale that to a much larger area? Now there's various problems in doing this, but let me just mention one, and that's again a computational issue, because this level of detail in a model means that actually it takes us several days to run this model just for one plot. And so upscaling it to a catchment where we might have 1,000 or 10,000 of these plots is completely impractical. So what we have to do is we have to take a very complex physics-space model and we have to turn it into something that people can actually use, people can run on their computers in a few seconds or a few minutes. And what we found is that actually this is relatively easy. We can take a very complex physical system and represent it quite well with a very simple conceptual hydrological model. And then we compare the outputs from each of these two different types of models, and we conclude, if we look at it relatively superficially, that the simple model is sufficient. So this is what a lot of people have concluded in the past, but what we've been doing is trying to dig a little deeper and actually think about what kind of errors this is introducing. And one of the things it does is, if you actually start looking at the rehabilitation strategies and you look at the changes in hydrology and water quality that these different strategies are having, you find that the ability of this simple model to represent these changes is not actually as good as the superficial comparison results might tell you. So actually, these are just various examples looking at different rehabilitation scenarios, looking at the differences between what's predicted by the complex model and what's predicted by the simple model, and we find that there is some skill there, but it's not as good as we had hoped. So there's more research to do on that. Now going up to larger scales, what I talked about there, peatland rehabilitation, is actually quite an intensive process. So a PhD student for 3 years just looking at this one catchment. But of course, practical problems require us to look much more efficiently at much larger scales involving whole regions, multiple catchments. So this is just introducing some work that I did a few years ago with colleagues at the University of Melbourne and CSIRO here in Australia, looking at how we can efficiently do much larger scale hydrological modelling over parts of Australia. So the idea is each of these black dots represents a flow gauge, and so we look at the variability of flow at each of these gauges, and we try and explain that variability using observable physical characteristics of these catchments. And the idea is, if you can do that for all your gauge catchments, that allows you to predict what the variability will be in any other ungauged catchment in Australia, so long as you have got some measurements of the catchment skill properties there. Now, we've done a lot of work on this in the UK as well, and another interesting contrast between the UK and Australia is that is the size of the UK compared to Australia, and each of these black dots represents the gauges that we use to do this in the UK, and you can see that really we've got a wealth of gauges in the UK compared to the density of gauges that you're able to use in Australia to do this type of problem. So that's another interesting aspect to do with the scale of Australia and how much less well established your flow gauging network is here compared to the UK. Now, unfortunately, what's happening in the UK is they've looked at other countries like Australia and said, you know, actually, most countries have only got a 10th of the number of gauges we've got, so they're actually starting to thin out the number of gauges in the UK, unfortunately. Okay, so just a summary of that. Global and regional climate models, not yet very good at estimating rainfall, so there's a lot more work to be done by our climate modeling friends. So we use statistical downscaling, which is essential for us hydrologists, but it does produce very high uncertainty in general. Hydrological models, we are moving towards much more complex, high-resolution distributed models, but there is a problem that they're really not yet supported by our knowledge of processes or by our observations. So there's fundamental research to be done on measurement methods, process knowledge, upscaling of local impacts, and regionalization of hydrological responses. Now, I've just got one slide just to put this back into context, that ultimately what we're interested in is risk. Risk to our mines, risk to life, risk to infrastructure systems. And so we have to take our hydrological variables and actually look at what impact they're having on infrastructure, social systems, etc., etc. So this is just some illustrations of that. So this is floods from 2007 in the UK. So the risk here is not just to this electricity generation station that's been flooded. The risk here is to all the other infrastructure systems which are connected to this electricity station. So it really becomes a complex network analysis problem, looking at the knock-on effects of the flooding right through the network of infrastructure. This is your recent floods in Brisbane. So this is the wastewater treatment works, which has been flooded. And in this case, of course, not just the damage to the wastewater treatment works, it's the environmental knock-on effects downstream because of the contamination coming out of that works. So some of the research we've been doing recently at Imperial College was looking at coupling our hydrological models with these complex infrastructure networks and looking at the knock-on effects of the risks, and then how we can introduce some flexibility into our infrastructure networks so that that risk does not get propagated so much through the system. So I'm going to conclude just with some points of the relevance, potential relevance of all this for the mining industry. Now I came up with about 20 points, but I've condensed this down into 3 quite general points. The first one is identification and attribution of hydrological change. So we are living in a hydrological system that is characterized by this image here, where we've got trends, we've got random variability, we've got cycles. Now, of course, when there's a major mining project, suddenly everyone becomes interested in hydrology and water quality and the impacts. And of course, there is a danger that you're potentially at some point on the system, like here, and suddenly people start observing these random changes, or these cycles, or these trends, which may or may not have anything to do with the mine. And really, it's a significant hydrological challenge in disaggregating the various potential effects on the hydrology of the catchment, especially given that many of these areas really haven't been monitored well in the past. Secondly, most hydrologists are, or at least they should be, interested in the communication of the science. It's no good looking at a problem and presenting to an audience and talking about my P statistic says that this mine isn't having an effect at 99% confidence interval. You need to be able to present that in terms that stakeholders understand. And that itself is a significant education and research issue, how to do that. And thirdly, planning under increasing water security issues. The nature of variability of hydrology is changing. It's not necessarily changing for the better. There's going to be more floods, there's going to be more droughts, there's going to be more competition for dwindling water resources. And really the first step in managing this is actually quantification of the problem. And I see hydrology having a big role in the research